So this is part one of acid, base and buffers, buffer calculations. Quite a lot of buffer calculations, and as you can see, I'm wearing another t-shirt today. And again, backwards, if you can read it, I wear this shirt periodically. Okay, you can get these off a certain website. Okay, so please enjoy your chemistry t-shirts. Now, this is part one. And we're going to remind ourselves of a buffer solution. Keyword there, minimises. Okay, so keyword minimises, really say minimises, small amounts of acid or base. So a buffer solution, one that minimises pH changes on an addition of small amounts of acid or base. Now, type of calculations on buffers. Part one, what is a buffer? Okay, we're going to do MCQs and short answer questions on that one. Okay, there can be up to 6 marks, to be fair, mostly 4. Okay, and then part two, we are going to do ratio and concentrations, what makes up a buffer of a certain pH and things like that. And then part three, what's the best choice for a weak acid to make a buffer of a certain pH. Okay, so part one, part two, part three. Okay, and let's go to the next one. So this is all going to be based, our calculations, on the acid dissociation constant. So when it dissolves in water, you get this equation, H plus and A minus, the conjugate base A minus. Okay, and then from there you get the Ka equation. So the Ka equation is this, and you can see it here, products over reactants. Okay, and this is what you're going to use to calculate your pH by finalising and finding out what the H plus concentration is. Now, the position of the equilibrium depends on the strength of the acidity of the acid. So the strength of the acidity of the acid, okay, and therefore higher concentration or lower concentration depending on that strength of H plus ions. Now, remember Ka remains the same for each acid, it only changes with temperature, and in these questions you are most often going to have it just at the same temperature, and Ka will remain the same for each. Now, we'll look at our first one, using the Ka constant to calculate the pH of buffers. So, the first one we're going to do is talk about a weak acid and a conjugate base used to make a buffer. So if we do that, the A minus is the conjugate base concentration and the HA is the weak acid. So remember there's two, and I'll go over here and just do this. Remember we're adding these two solutions. That is your A minus number of moles. So you can work out your number of moles of the conjugate base, and then this is the number of moles of your weak acid. And then we calculate new concentrations when we add it together to the buffer, but I'll show you how to do that later. But really important, A minus is your conjugate base that you're adding, and HA is your weak acid. Now let's go straight to a question. So with the question, buffer solution was made by mixing 50 centimetres cubed of 0.3 moles per decimetre cubed ethanoic acid. So that means you can calculate the moles of the ethanoic acid because you have the volume, you have the concentration. Again, stop the video and do that. Now, you also have sodium ethanoate. Sodium ethanoate is the A minus. It's the conjugate base of ethanoic acid. Well, the ethanoate is the conjugate base of the ethanoic acid. So this question wants to know what's the pH, and it gives you a Ka value right here. Let's move it to the side, okay, and bring our equation back up. Okay, now if that's the case, we want to know the H plus. We can, because we've got 50 centimetres cubed and 0.3, and because we have 100 centimetres cubed and 0.6, we can work out the moles of the sodium ethanoate, the moles of the ethanoic acid. Okay, now, the important thing for you to realise is that they're adding this together. So they're adding this together. So 50 is being added to 100. So this is the key you have to do in a lot of these equations. A lot of the equations are going to have separate solutions which you then have to work out the moles of each one. And then you have to calculate the new concentrations once you've added the two volumes together. So the total volume of the solution is 150 centimetres cubed. So we work out the moles in each one of them, and then we use the volume, the new volume, to work out the concentration of A minus and HA. I'm going to show you how to do that now, okay? Before we go and do that, what we do is we have the equation, and in the equation you can see that I've just rearranged it. I've taken the Ka here, and I've times it by HA, and then I've divided by A minus. So just rearrange it to equal H plus, because once it equals H plus, we can use pH equals minus log of H plus concentration. Now, so that's what we need to do. So let's do the first part. So the first part is the number of moles of the acid. we have got a volume, which is 0.05, which is 50 centimetres cubed. 50 divided by 1,000 is 0.05. So that's that, times by the concentration, gives you your number of moles of the HA, or the acid, ethanoic acid. We then go for the next one, and the next one basically is CH3COONA, and we know we've got 100 centimetres cubed, which is that one, times by the concentration, and then this is your number of moles. So we've got a number of moles of each one, the HA and the A minus. Okay, so we've got the number of moles of these two here, that one and that one. Okay, now if that is the case, we can then turn them into concentrations. They're moles at the moment, they're not concentrations, so we need to turn them into concentrations. And the concentration is based upon the total volume of the solution, which is 150. Now if you have this equation, which is those green ones over there, if I go over here, I'll just show you, we're just rearranging it here. So we've got the number of moles, and we're dividing it by the new volume. The top one is the volume times concentration, and now we're rearranging it, number of moles divided by volume will equal our new concentrations to put into our equation. So there we have, we've just taken this, our number of moles, which is here, divided by our new volume, which is 150 centimetres cubed, or 0.15 decimetres, and we have the other one here. So we've got our new concentrations of our HA and our A minus. Now let's move that out of the way. So we've just kept our concentrations now, so we can put it into our actual calculation. This is where I'll come in with a pen. Okay. So what we've got here is we have Ka, and we know Ka is 1.75. So 1.74, sorry, times 10 to the minus 5. Okay, so 1.74 times 10 to the minus 5. And we got that from over there. Times by the HA. The HA is the acid here, and that is 0.1. Okay, and then you divide that by your A minus. Your A minus is 0.4. Okay, if that is the case, that adds up to 4.35 times 10 to the minus 6. So 4.35 times 10 to the minus 6. Okay, so we've got our essentially our H plus concentration, and all we have to do now is put it into pH. So pH is equal to minus log of 4.35 times 10 to the minus 6. Okay, and if that is the case, that will equal a pH. Let's get a different colour here. That will equal a pH of 5.36. Okay, 5.36. Notice to 2 decimal places. And that is the most typical question you'll get. So there's a simple way of practicing this. So if you can do it once, great, but need to do it a few times. And it can often be an MCQ question where they give you different options. Okay, so what you can do is you can just change these numbers. So just change the numbers. Make that 75. Make that 125. Make that 0.6. Make that 0.8. Just change the numbers around and practice it a few times, okay, to get it into your head. And that is how you can calculate the pH, okay, of a buffer using your Ka, Ha, and A minus. So in our next question, we've got a buffer solution based upon ethanoic acid again. And in the buffer solution, the CH3COO concentration is half that of the CH3COO minus. So that is half of the other one. Now you label that as HA and label that as A minus, and you can start to get the point of the question. And we need to know the pH. So let's move that to the side. Okay. And now we've moved it aside, highlighted the key areas. So that half. Okay. Now what you've got to remember is this. When you look at this, this is Ka times Ha, right? Which basically means, if I do this, it's just a ratio. So I could write it out like this and do Ka, and then that'll be times by Ha. So Ka times Ha, and that Ha. Okay. So that there we have that equation, and that's equal to H plus. Okay, so we've got that equation. That means that's simply a ratio. Okay, so it's simply a ratio. So what we can do is we can manipulate this and we can go, right, all right, so we will just put the numbers in now. So we can just put the numbers on 1.74 times 10 to the minus 5. So 1.74 times 10 to the minus 5. Okay, and then we're going to times that by these numbers. So we know that HA, so we look at HA and we go, okay, the HA, CH3COO minus, is half that of the CH3O. So the HA, okay, is at the top, and it's half that that's at the bottom. So we just make that 0.5. Okay, we can make that 1. So that's, because it's a ratio, because it's a divide, so it's a ratio. So my 5 is really rubbish there. Okay, so if that's the case, you can just put that into the calculator. Remember, that is going to equal H plus, and it equals 8.7 times 10 to the minus 6. Okay, that's 8.7 times 10 to the minus 6. So we've got a H plus concentration. And all we then do is put it into our pH calculation. So pH calculation is going to be equal to minus log, and we've got a H plus concentration. H plus goes in there, which is 8.7 times 10 to the minus 6, which gives you a beautiful pH of 5.06 to 2 dP. Okay, let's make that drawn. Okay, 5.06 to 2 dP. Let's make that a little bit clearer. Okay. Okay, so there you go, 5.06 to 2 dP, and that's how you do this question. Our next question is calculating the pH of a buffer, and I've just forgotten to see whether, oh, we are recording, so it's all good. Right, so to prepare a buffer solution, 75 centimeters cubed of the propanoic acid solution with some sodium hydroxide. So this is when we have an excess of weak acid and a strong base. Now, if you look here, we're calculating the pH of the buffer at 25 degrees Celsius, okay, and we're giving our answer to 2 decimal places and showing the working. So let's move it all the way across. Okay, and then we have got our acid plus the base here. Okay, so this question is a lot of working out and can give you quite a lot of marks. So let's start going through it. So to prepare a buffer solution, we need propanoic acid and we need our sodium hydroxide. Now we're given a volume and we're given a concentration and volume, okay? So we're given a concentration and volume, so what we can do is we can work out our number of moles. I haven't got a lot of space here, and during this video we've worked out moles before, so that's volume times concentration. So what we can do is work out our number of moles of each. So let's put moles here, and then just go across, and just write down what our moles is. So our HA, our moles is 0.0165. Okay, so we worked that out by doing volume times concentration. So 0.075 times 0.220 gave us this number. We then work out our sodium hydroxide. Our sodium hydroxide is 0.00925. Okay, so 0.00925. So we've got those two numbers. Right, now this is the really important thing. This is a 1-to-1 ratio. So 1-to-1 ratio. And because it's a 1-to-1 ratio, that means that this is in excess because there's more of this than that. So this will react, 1-to-1 ratio. That means you'll use up all of this, and in the end, and I'll say end here, this will be 0. Because it's all used up, okay? So it's absolutely all used up. Now, that means we can work out how much is left of the acid by taking the original, which is 0.0165, and minus 0.00925. Okay, so taking that away because that much has been used up because it's reacted with the sodium hydroxide. Which then equals, and that's our acid remaining, okay, is going to be 0.00725. Sorry about the squeaky pen. So 0.00725, okay? So this is our acid remaining, okay? We've used up all the sodium hydroxide, okay? And then we go across here, and then the ratio continues, okay? So the ratio continues. So that means basically, if we're looking here, it's then a ratio of 1 to 1 again. Okay, I'm not worrying about the water for now. It's 1 to 1, and this is our A minus. Okay, if I've used up all of this is the limiting reactant. So I've used up all of that, and it's a 1 to 1 ratio, and therefore I'm going to make, on this one, 0.00925. This is like your ice tables. Okay, so it's like your ice tables. So the initial here would have been 0, and then we used all that up, and then we've made 0.00925. Okay, so we've got this, and we've got our number of moles, okay, from that. So what we then have to do is calculate the concentrations. Okay, so calculate the concentrations. Now, if I'm calculating the concentrations, okay, that basically means that what we have to do is take those number of moles and we divide it by the total. Okay, so divide it by the total. So what I mean by that is your moles divided by your volume. So we've got our number of moles, which is that. We now need to divide it by a new volume to find our concentrations. And we did this in a previous question, so I'm not writing it fully down. So you can look at the total, it's 50 plus 75 centimetres cubed, which is 125 centimetres cubed. So if I want to do concentration here, it's going to be moles, which is 0.00725, okay, divided by 0.125. That's 125 centimetres cubed. Remember, I'm doing this in decimeters. Okay, so that's my moles divided by my volume, which gives you a concentration for this. Okay, so my concentration of this is 0.058. Again, you can stop the video at any point and do the rest yourself. So if we go across here, okay, we're now then going to do the concentration of this, which is our A minus. Now the concentration of the A minus is going to be this number divided by the total volume, which is 0.125, and you will find out that that is 0.074. Okay, so remember these are concentrations. So this is moles per dm cubed, and this is moles dm cubed. Okay, so that's moles dm cubed. So we've got our concentrations now. And all we have to do is use our Ka. So we've got Ka already arranged up there, which is nice. And all we need to do is put our numbers in. So we've got our Ka, which is 1.32 times 10 to the minus 5. Okay, 1.32 times 10 to the minus 5 is going to be times by HA concentration, which is here, 0.058. Remember, we're just doing that equation at the top there. That has to be divided by A minus. Now the A minus is 0.074. Okay, so that's divided by 0.074. And then that will equal 1.034 ... times 10 to the minus 5. Remember, you keep all the numbers in the calculator. Okay. Then you calculate the pH from that. Okay. So if you can put it in your calculator now, I'm going to quickly just scroll down. And that means you can put pH equals minus log, okay, and that will be 1.034 times 10 to the minus 3, which would equal 4.9922 dP. Okay. So think about how much working out you've got to do. You've got to work out the moles, which will get you 1 mark. Work out the concentrations, get you another mark. Okay, new concentrations. Okay, it might even get you another mark for working out the moles at the start and working out the difference in moles once you've taken into account the sodium hydroxide. Okay, so maybe 1, 2, 3, 4, putting it into the equation, 5, working out putting it into the pH, and 6 maybe to get the final pH. So this is a monster question, okay? So practice. Again, if you practice, very easy to practice, all you do is you take the HA and make sure there's more of that than the sodium hydroxide, and just change your numbers around. And you can practice this as many times as you want. Or if you're feeling like you would just want to use ChatGPT, you can put the question off this into ChatGPT and say, give me some more questions just like this. Okay, and you can get that to generate questions for you so you can practice. But this does need a lot of practice. Hope you enjoyed. Okay, so this question is really about understanding the essence of the Ka equation, really. So more water was added due to an error, so you made a mistake. Suggest that the pH of the buffer solution will be the same, greater or less than. Okay, and you need to give your reason. Okay, so put it to the side again. Okay, and then we've got this. So if you look here, it says there's an amount of water that was added. Now, first of all, that amount of water that's added, okay, is going to affect the concentrations. So if we just separate it out a little bit, just to make it a bit simpler to understand, you can see here that it would dilute this and dilute this. That's how you calculate your H+. So you're calculating this. So it would dilute this and dilute this, which means it would change both of those by exactly the same amount, which means the change would be cancelled. So your H+ would be exactly the same number. Okay, would be exactly the same number because it's just a ratio. So the ratio and proportion of HA2O- is the same because of this division here. Okay, so it doesn't matter whether you added a little bit extra water. It's added to both, which means it would cancel. Okay, so the pH is the same because that's based upon the H+, and the H+ would be the same. And so that is your answer to your question. So in this question, we've got to calculate the pH of the buffer, but we're given masses. Okay, so all we have to do is calculate the moles first and then go into it. So let's put that to the side. Let's remind ourselves of the equations again on the side, and then what we can do is write it out. Let's see whether you can write it out as quickly. So I reckon you can, if you've looked at the first two, you could probably work this out yourself. So stop it and try to do it yourself. So basically what we've got to do is we've got the number of moles, and I'm going to shorten it to say HA. Well, the HA just meaning your acid. So your acid is propanoic acid. Okay, so all we're going to do there is just say 18.5, because that's how much grams it's given us, divided by 74. And that is 0.25. Okay, and that's your number of moles. Now, if that's the case, we then have to do our A-. And again, I'm going to shorten it to A-. But this is the conjugate base. The conjugate base is a sodium propanoate. So that's 12 grams of that. And if you do the molecular mass of that, you'll find that that is 96. And if that is the case, that's 0.125 mole. So we've got a number of moles of each of them to start off with, right? Now we need to work out our concentrations, and our concentration is going to be concentration, and I'm going to do HA first, and I'm going to do my concentration of my A-. Okay, and if we do that, we know our moles divided by volume, as we've done in the previous ones. So that means we do 0.25 moles divided by our new volume, our volume, okay, because it's just not a new volume, it's made up to 250. So that's 0.25 divided by 0.25, okay, because that's in decimeters, which means 0.25 divided by 0. Is a nice number. It is the number 1, okay, and that is our 1 mole dm cubed, okay. And then we go here, and we take our 0.125 divided by the new one, which new one is again 0.25, which will equal a nice number again, which is 0.5. Okay, so we've got that. So we've got our concentrations. Now all we have to do now, okay, is put that into the calculation, because we've got the Ka equation. Okay, but we also need to do something extra. We've been given a pKa. Because we've been given a pKa, we need to convert that to Ka first. So it's a little complication. So Ka is equal to 10 to the minus pKa, which means 10 to the minus, which is 4.87. Okay, which means, if we carry on, 1.348 times 10 to the 5. And again, and that is times 10 to the minus 5, sorry. Okay, and therefore I have my Ka. So my Ka value, I've got all my concentrations. I'm not going to write this all out again. You put it in to the Ka equation. Remember, the Ka equation should be equal to H plus, which is going to be equal to Ka times the HA divided by A minus. Okay, so that means you get your H plus, and if you get your H plus, you should end up, and then put it into pH minus log, as you've done in all the other ones. Okay, and if you do that, you will end up with a pH of 4.57. So if you're not sure, stop the video and put them all in. Remember, you are putting it into this equation, which is H plus equals Ka times HA divided by A minus. Okay, so all I'm doing is taking that number down there, putting it into here, taking these two concentrations here, put it in there, get the H plus, put it into pH. Let me just make sure you know, just in case anybody's not sure. Okay, put it into pH equals minus log, and you will get a lovely pH of 4.57.